Hello from my side as well, and welcome to today's webinar on explainability for human-AI collaboration. I am Philip Mavropis from the University of Piraeus Research Center, and I would like to thank you all for being here. So before we start, I would really like to go over what HumAIne is. And HumAIne actually aims at the creation of a human-centered platform for trustworthy human-AI collaboration in a dynamic and real-world environment. Right now in HumAIne, we have four AI paradigms: active learning, swarm learning, neurosymbolic AI, and human-centered explainable AI. Today, we'll talk more about human-centered explainable AI, but we have some excellent webinars already on swarm learning and neurosymbolic. Of course, as a cornerstone of the project, we have human in the loop by design. AI systems should learn from human input, feedback, and domain knowledge instead of just being black boxes. And the paradigms that we have in the project are applied in unstructured and dynamic environments across multiple domains: smart energy, smart ticketing, smart healthcare, and smart manufacturing. Today with us, we have also Kostas from smart energy, but we will also see some minor demo from smart healthcare. And to jump in a bit on what explainable AI is. As explainable AI, we define the set of processes and methods that allow humans to comprehend and trust the results and output created by machine learning algorithms. Here, I want to stress out a few words. So it's a set of processes, not just one thing. And also, it not only allows us to comprehend, but to also trust what is coming out of the machine learning algorithms. So it's not just about the math being right. Even though most of the discourse around AI revolves around better accuracy and better prediction. But it's about being able to verify why something is right. To make that more clear, let's take a look at the center of the presentation of the slide. We have traditional AI, where you have input data and then some hidden process, often called the black box, and then an output. So now you know what is the action that you need to take, but you have the reasoning being locked away. On the other hand, we have explainable AI, where the input data remains the same, but the system analyzing it is transparent. So now you not only have the output, but you also have the explanation, the why. So you're moving away from knowing the what to understanding the why. To achieve that, you have three pillars of explainability. Of course, in literature, there are way more, but we will focus on those three today. Interpretability, which means, does a human understand the internal mechanics of the model? If the model is too complex for a human to follow, then essentially it lacks interpretability. You have also transparency, meaning, are the data, the model architecture, and the logic for the whole decision-making process open for inspection? And of course, last but definitely not least, you have trustworthiness. So does the user, with a given explanation, feel confident enough to take an action? Whether you're a doctor, whether you're someone trying to approve a loan, or anything in between, you need trustworthiness. And now we essentially more or less established that explainable AI is the transparent system that helps us move from blind trust to informed confidence. But how do we build it? As always, it depends. It depends on the problem complexity, the data that we are using, and many, many more things. But generally, there are two main pathways we can go, two main categories, if we like to say. We have glass box models on one hand, which are transparent by design. They are easy to understand. And we have post hoc explainability that allows us to explain and extract understanding from models that would otherwise remain as black boxes, such as neural networks and more complex models. So if we focus a bit on glass box models, as I said before, they are supposed to be, and they are, explainable by design. So on that category, we have linear models, where the same weights of the model are explaining the feature importance of each feature that is contributing to the model. And we have also decision trees, where you can follow a simple if-then rule set, let's say, to understand why the model believes that a certain prediction is true. Additionally, we have some more advanced glassbox models, such as GAMS, generalized additive models, where they are able to explain more complex relationships without sacrificing the explainability of the model. Here, usually there is a trade-off between explainability and performance, but I say usually because GAMS is quite a nice example on us having the best of both worlds. And of course, more research is focused towards that area, making glassbox models that are also performant. On the other hand, we have post-hoc explainability on the right side of the screen. And here I will guide your attention to the matrix that we have below. So on the vertical axis, we have model-specific and model-agnostic, where essentially model-specific means that this method or process needs access to the internal workings of the specific model, whether it's its architecture or the gradients or whatever. It needs specifically access to the inner workings. For example, GradCam utilizes the gradients of the model in order to showcase the activation and what led to a specific prediction for a neural network. And on the other hand, you have model agnostic processes. So model agnostic processes essentially treat the model as a black box, and what they do is that they change the input data in order to see what is happening to the output. And by that, they infer some explainability. In that category, we have some really famous XAI techniques such as LIME and SAP. Now, on the horizontal axis, we have local and global. And what this means is essentially that for local, we mean that we will explain one specific data instance, one specific data point. And we will deep dive on why for that specific data point, we believe the prediction is as such. While on the other hand, for global, what we do is that we try to get more understanding on the model itself. So with that being said, I believe we can proceed on how we are approaching human-centric XAI in HumAIne. So our approach isn't just a single tool, but an entire ecosystem, I would say, designed to make complex models accessible and actionable for everyone. So we are starting with Explain on the top of the slide, where one of the biggest challenges in XAI is that even explanations provided by some processes of XAI, such as LIME and SAP and so much more, can be still complex enough that requires data science understanding, that data science background for understanding. So what we achieved here is that, and that was back in 23-24, where LLMs were just starting to pick up, we got the output of XAI techniques. We used a specifically tuned and instructed LLM in order to take the output of the XAI and create natural language explanations. And essentially, this system provides plain language, actionable insights, and accessible to non-technical users. This is the most important thing. Then moving on to the virtual XAI, the problem here is that not all techniques are suitable to all the problems. As we stated before, it depends on the problem complexity, on the data that you're using, etc., etc. But a slightly non-technical user won't be able to make that distinction. To that end, what we try to do here is that we used quantitative and qualitative evaluations through both benchmarking XAI methods on their fidelity, accuracy, and some other technical metrics, while also using some virtual personas. So here we constructed 100 different diverse personas and made them answer on their preferences for specific XAI methods. And based on that, we extracted the knowledge of the system and we allowed the user to use that in order to identify the most appropriate method for their needs. Then, building directly onto it, we have human-centric chatbot. Here, we took the virtual personas from Virtual XAI, and with some help from our multiple partners from HumAIne, we were able to build HCC. This essentially is a chatbot that utilized reinforcement learning in its training in order to understand the user needs and adjust both like the style, the tone, the depth and the brevity of the answers, let's say, or the complexity on the fly, to ensure that the explanation provided by the chatbot resonates well with the end user. So that was a big achievement, I would say, for HumAIne. And then we have on the other side of the screen the HGBD library. So this is the HumAIne Glassbox dashboard library. This library is for the general needs of people building models or interactive dashboards, which is based upon on open source project of Explainer dashboard. As we will see later on in the demo, it allows users to create their own model, providing wrappers for major libraries such as scikit and pytorch, and build their own dashboards for a collection of components. Additionally, users can create their own custom components in a straightforward way for their needs. Since that was a later development in the project lifecycle, what we did is that we took Explain and created it as a component for HGBD library, making it available by default to all the users of this library. And next, we will talk about HumAIne CBM, which is essentially to address the needs of analyzing tabular data specifically. We utilized HumAIne CBM. This is based on the tab-CBM approach, which is designed to extract concepts from raw tabular data. Most of the times, what usually happens nowadays with big data and more data collection and all that is that we end up with some data sets that are sometimes too expressive, let's say, or they have too many features that are really hard for us people to understand the interactions, how are they linked together, what they mean, and everything like that. So this HumAIne CBM approach utilizes the features, and we will see that later on in demo, and creates concepts, high-level abstract concepts that help the user understand why a prediction is being made. And finally, we're integrating neurosymbolic AI, which aims to combine the learning power of neural networks with the formal logic of symbolic AI to create models that are fundamentally more transparent from the ground up. Of course, I will not talk about neurosymbolic AI today because there is a whole webinar revolved around. And now this is a really high overview of how we plan to integrate with external systems. It all starts with the data owner, where they publish their data into HumAIne's data storage, which is a Minio instance. And then essentially, the ML engineer can then start either by training a new model based on the data or load the trained model. And this happens within the HGBD library, which is hosted on a Kubeflow instance on our HumAIne platform. And HGBD right now is offered as a Docker image, which makes it easy to deploy everywhere. Once you have the trained model ready and you're happy with it, let's say, you can involve in the process the domain expert, someone who has to interact with the result of the explainable AI to make decisions. And then you configure the dashboard and the XAI, what you need out of it. You might need SAP, you might need PTP, everywhere, everything. So once you have that, you can push the results or even the dashboard itself back to the data storage, which is then becomes accessible either to either internal systems of HumAIne or external systems of pilots. One example that we will see here from Costas is such an external system. So now I would like to move to a demonstration for HumAIne CBM, for smart healthcare. And so what we see here is that the user uploads their data and they have all these different features for medical data. And we can build quite a nice model onto it, like with really good accuracy. Of course, this is a TOE example, thus that huge accuracy and those F-scores and precision, etc., etc. But this is not the point of the demo. Here, what we see is that we can discover concepts. And as concepts, as I said before, we have collection of raw features present in the dataset, but aggregated in a way that makes sense. So right now we have concept one, which is triggered mostly by sleep mean, by the max steps, etc., etc. And you can, of course, change the number of concepts that you want to have, or the number of features that participate in a single concept. But this, I would argue, is not explainable. I don't understand that concept one is something, concept two is something else, but I have to take time to understand how those are connected. So what we did here is that we employed LLM support here in order to give the concepts corresponding names. And here we will see that now we have the same concepts, but with readily understandable names: sleep and activity balance, steps and sleep consistency. And we see that this is quite easier to understand. What we can also see is that we have some descriptions based on the actual raw features that were used for describing each and every concept. And also, we have some relatively simple examples where we have a positive class example where the true label is 1, so we have a positive prediction, and also the model is really, really sure that we should have a positive prediction. And on the other hand, we have a negative class example where we have a negative prediction, and the model is also sure that we should have a negative prediction. And here we can contrast and compare what is the difference in the activations of the concepts for those two data instances. And in order to have it a bit more easy, we can check that the largest concept activation gaps are in sleep quality and goal achievement. So essentially, this allows us to go from really, really big datasets with many features into easily explainable concepts that help us guide understanding for our predictions. Great. And then I will move to the next demo to HZBD for smart energy. Here, and Costas, I will try to not spoil that much, but some general ideas is that one of the use cases that the smart energy tries to do is that we want to have 1 day ahead prediction for the grid load of the power grid for Greece. And here we've built different models based on the different horizons that we are trying to predict ahead. And each and every model has its own dashboard because, of course, different models have different interactions, different feature importances, everything. So here we can go into the 1 hour ahead model analysis where we can see feature dependence, regression stats, all of them are interactive, and some individual predictions, of course. And what is important is that those are some components that we chose to have here. They're by any means an exhaustive list, so there are many, many more. Here, for example, you can select one specific instance, so that would be local explainability, and features to see how we arrive at the final prediction of the model based on other features. I know it's not really visible, but the bars, the green bars, show positive contributions of specific features, and the red bars, negative contributions of those features. And we have that, of course, in a table as well. So now we're going to see quickly, and don't worry about the API key, that will be disabled immediately afterwards. So right now we can say that we have for feature importance, this and this, and we don't really know how we are supposed to analyze. And here again, what we did is that we take explain, created a component as a dashboard component here, and ask for the analysis. And here we get a direct assessment of what is happening, dynamics, risks, and actions. And we can also ask follow-up questions, enable an interactive experience with our own explainable AI methodology. So right now, this is all from my side, I would say, in order to not take too much time from Costa's presentation as well. But one thing I also want to stress out is that this is built interactively in Jupyter notebooks. So this allows the user to create anything they want. And also, you don't have to serve that as a dashboard that is hosted somewhere. You can also take individual results from XAI techniques, push them back to the storage, the data storage of HumAIne, and then make them accessible to anyone that needs them and has access to them, of course. So I believe that's all from my side.
Great, great. Well, thank you very much, Philip, for the overview from your end. And while I ask Kostas to start preparing your slides, I'll also remind our participants today that if you have any questions, either for Philip from this first half of the session, now would be a good time to ask, or also to use again the chat feature to put your questions there.
Okay. Now that Philip gave us the big picture of the XAI component, we will try to dive into how we use it in the Smart Energy Pilot. The outline of the presentation is the following. I will first try to explain how and what how we use the HumAIne components in our Smart Energy Pilot, and what in general is the Smart Energy Pilot and what we are dealing with. Then we will try to explain why do we care about XAI in general in the power system operations. Then we will try to make it specific how we use the XAI in the context of our Smart Energy Pilot. I will explain how we are integrating from our end to the XAI component. Then I will go metric by metric to explain what they are and what is the added value for the system operator. I will provide a demonstration of our smart energy dashboard. Then I will talk about some potential application beyond HumAIne, potential application of XAI beyond HumAIne, and I will conclude with key takeaways. So in the right screen, in the right picture, we see how the control room, which is actually the room that the system operator has access to screens of the smart energy of the transmission network, and it's actually the room that our solution fits into. We see how it evolves through time. We see that as data grows, and as the power systems and the smart energy becomes more uncertain with the inclusion of the renewables, the system operator moves away from being reactive at real time, and it moves to operational planning by being proactive, which means that The system operators need to anticipate different outages in the grid, different events that might happen. The processes from manual become more proactive. We need, in general, instead of having different screens to be able for the system operator to check different screens, to include some notifications, to get the attention of the system operator in case something happens. And also, since the smart energy infrastructure is a safety critical infrastructure, here the system operator needs to be very careful. The traditional methods that they use that are based on deterministic models, since the data become grow, these methods become insufficient. But on the other side, the operators distrust the AI solutions because they feel that something as a black box. What we have decided to do in HumAIne is to create a parallel system with the actual legacy infrastructure that allows operator to run scenarios using a power grid digital twin. We integrate from the HumAIne components the human-machine interface for the intuitive interaction with the power grid and the digital twin. We provide explainable AI insights for the day-ahead total load forecast, and through active learning, we are trying to improve the operational efficiency by optimizing the data labeling efforts. Our approach and the collaboration here is human-centric, which means that the operators retain the primary decision-making authority, and the AI acts as a complementary assistant, providing insights and recommendations. Why do we care about XAI in the power system operations and the energy systems in general? The power system decisions are safety critical and time sensitive, with a direct impact on the grid reliability and the security. The modern AI models deliver high accuracy, but they are based on some black boxes methods, which limits the confidence of the operator. So the system operators need to understand why a prediction is made and not just what the prediction is. The lack of the explainability hinders the trust, accountability, and adoption of the AI-assisted tools, and creates a burden for the system operators to adopt them. So we are trying with this XAI to have high performance together with the human understanding, and to trying to bridge the AI world with the energy systems world. Within our pilot, we have decided to focus on the day-ahead total load forecast, which is an important metric for the transmission system operators. We have integrated this model into the digital twin operations and in our dashboard. And we have performed the metrics for the XAI explanations per time step. And on our dashboard, we have the operators that they can inspect the day ahead total load forecast. They can choose which time step they need to focus on. And then we provide all the available XAI plots coming from the XAI component of the HumAIne. So with this way, XAI supports us and consequently the system operators to have a better interpretation and informed decision making. Now we will move to the integration architecture. Philip showed before how the integration takes place from the XAI component till min.io. And here we will show the other part of this approach, which is from our smart energy pilot to to the XAI component. So each day we will upload the daily operational data to the MinIO from the Smart Energy pilot, especially to the Smart Energy data bucket. Then the XAI service retrieves the relevant data for them to perform their forecast. Instead of the forecast, they provide some XAI plots and they upload it to the Smart Energy Results MinIO bucket. And then at each day also, we retrieve both forecasts and the XAI plots, and we store them in our local database, and then we show it to the system operator dashboard. I will try to go metric by metric to see what is the operator value and try to explain them a bit. So the first one is the feature importances, which shows which variable have the most influence in the forecast, highlights dominance of the recent load history. The operator understands which signals drive predictions and detects abnormal reliance on unexpected features. Then we have the forecast contributions, which tries to decompose a single prediction into feature level effects and shows positive and negative contributions. The value to the operator is it sees why the forecast increased or decreased and enables trust at the individual forecast level. Then we have the detailed feature effects. It shows the distribution of feature impacts across samples. We have a color coded by feature magnitude and reveals some asymmetric effects. The value that it brings to the system operator is that identifies regimes where the model behaves differently, and it detects sensitivity under high and low load conditions. Then we have the partial dependence plots. They show the average effect of one feature on predictions, and demonstrates monotonic or nonlinear relationships. And an example here is the effect of actual load on next hour load. It builds intuition about model behavior to the system operator and verifies the physical plausibility of the learned relationships. Then we have the residual analysis, where it shows the residuals plotted against the predicted values. It highlights periods of systematic under and overestimation. And for the system operator, it detects, the system operator can detect unreliable operating regions and informs confidence and risk-aware decision making. Finally, the weak spot analysis. We have an error heat map over the feature space. It highlights combinations leading to high mean absolute error. The value for the operator is that it identifies conditions where forecasts are less reliable, and it supports proactive mitigation and scenario testing. And now here we have a demonstration of the overall dashboard. We have here the registration page. We can log in with our credentials. We have here the card feed tab where the system operator can check different notifications. For example, we have here the security classification, which is another feature that I didn't mention here. Then we have the total load forecasts. That is important of our XAI component. We have all the XAI metrics here that I explained before. So if we choose a timestamp and an XAI metric, we can see the different plots that I mentioned before, and these plots are retrieved from the MinIO at each day. We have here the importances, features, the PDP plot, the residuals, and the weak spot analysis. As we said, these plots are directly being created from the XAI components Also, some other parts that we have in our dashboard is the visualization of different variables that we retrieve from the different APIs that we have. We have here also the digital twin where it's the Greek transmission network, and we can simulate different instances of the grid as well as different events. So if we move through the cursor through the network, we can see the important variables. And also, if we have any violation, we can check it in the notifications. We have also recently integrated an operator agent where it tries to run all the tools that we have integrated through natural language. For example, we could simulate we could do the same, but for not with natural language. Here, for example, we need to simulate for yesterday at 12 o'clock and to ask we will have any voltage violations. Then the agent identifies which tool to use with which parameters and provides a clear and short answer. Okay, here we can log out, and that's our dashboard here. Oh, sorry. Then how we could use XAI beyond HumAIne. As we understood, the XAI framework demonstrated for the energy pilot is domain agnostic and transferable. Anytime series forecasting or classification task requiring trust and accountability can benefit from it. Some applications related to energy system can be renewable generation forecasting, distribution grid congestion and flexibility forecasting. Also, energy market bidding and price forecasting is something that we need the explainability for the forecast and for the models that we use there. Some other domains that we could expand is the transportation and mobility system, the industrial process monitoring and critical infrastructure forecasting and control. In general, as we said, XAI enables the better adoption of the human-in-the-loop AI, and it can support regulatory compliance, auditing, and operator training in real-world deployments. Some key takeaways for our smart energy pilot and the KPIs that we have measured and we are continue to measure till the end of the project is that it improves the operator trust in AI, it enables informed human-in-the-loop decisions, and also makes the advanced model that might provide higher accuracy to be operationally usable and trusted by the system operators. And also, as we saw, it scales and it can scale across domains beyond the smart energy. So that was from my side. Thanks.